We're going to start off today by just giving you one multiple choice question. I'd like you to take a look at this one, please. And then I'd like you to give me the answer as multiple choice question number one, please. All right, take a look at the answers here. Looks like 2/3 of you said the answer is C. 22% of you said B. And then 6% of you said A, and 6% of you said D. So it looks like the answer is going to be C. Let's take a look at that now. It says a proton enters a magnetic field at a right angle to the field. Right angle means that all of the equations that we've learned are valid here. F is equal to QVB, mv squared over r, and so on. The alpha particle enters the same field at the same angle, but with twice the speed. Once in the magnetic field, both particles move in a circular path. We want to know the ratio of the radius of the alpha particle to the ratio of the radius of the proton's path. What did we say a day or two that we do whenever we see the word ratio or compare or something like that? What's the one word that we think of? Divide. Yeah, we want to divide. Now, do we divide the radius of the alpha particle's path by the proton's path, or is it the other way around? Rp over R alpha. Which one is it? Option number 1 or 2? Or does it matter? It does matter. And the answer is number 1. Why does it have to be R alpha over Rp as opposed to the other way around? Yep. Yeah, what are we asked to solve for here? It says, what's the radius of the alpha particle's path to the proton's path? So it's going to be alpha over proton. If it says, what's the radius of the proton's path to the alpha particle's path, then it would have been the other way around. Okay, so let's go with this one. R alpha over Rp. Now, we don't know what the value of R is. If we did, then we just simply divide the two. We don't. Let's get an expression for R. We know that Fc is equal to Fm, or mv squared over R. Let's try that again. Or mv squared over R equals QVB. V's cancel. R ends up being equal to mv over qb. Right? The R goes up by multiplying. The qb goes down by dividing. So let's substitute that in here for R alpha and Rp. Let's say mv over qb. That's all for the alpha particle. Divide that by m proton, v proton, over q proton times the magnetic field proton. It says it's the same magnetic field, so B is going to cancel out. It says it's twice the speed. So if the alpha particle is twice the speed as the proton, then if we want to, we can just replace V alpha with 2 times V proton. Does that make sense what I did there? Is that okay? Look, if it's twice the speed of the proton, then let's call it twice the speed of the proton. That way, at least we get the same variable in both the top and the bottom. What value does that have? To get the same variable on the top and the bottom. What does that allow us to do? Set it to 1, you could, or you could just cross it off, cancel it, right? Because V divided by V is 1. All right. Now we could put some numbers in here for M alpha, Q alpha, MP, MP. We could do that. Or we could say, wait a second. I noticed from my data sheet that the mass of an alpha particle is 4 times the mass of a proton. That gives us the mass of the proton on both the top and the bottom. And we could also say, if we wanted to, if we recognize this, that the charge of the alpha particle is twice the charge of the proton. Okay, if you didn't spot that, that's okay. Just plug your numbers in. But if you did, it allows you to cancel out that. Now we're left with no variables at all. All we've got at this point is some numbers. 4 times 2 divided by 2 is 4. That's it. So now the ratio is going to be what? If we solve this and we got 4, the ratio is going to be 4 to 1. So the answer would be C. 2/3 of you got C. How many of the people that did it, how many people did it by canceling out everything like I did? Okay, not very many. How many people did it by putting all the numbers in there for MP and QP and M alpha and stuff? How many people did it that way? Okay, that's fine. One way is not better than the other, for sure. Don't panic because you didn't do it my way. The only benefit to my way is it saves you a little bit of time and a little bit of effort punching it into your calculator, but it's not better. It's just a little bit quicker. Does this make sense to everybody else now? We did a question similar to this the other day, right? Not exactly the same, but similar to this. I think it was one of the, it was a worksheet question, I think, on worksheet number 12. Today we're going to move forward a little bit and talk, firstly, a little bit about electric current. Now, somewhere in the back of your mind, you may be thinking right now, electric current, we did electricity in our last unit, now we're doing magnetism, now we're going back to electricity? Kind of. Electric current is not a curriculum objective per se, but it's something that we need to know in order to cover a curriculum objective in a few minutes. The curriculum objective that we want to cover has to do with having an electric current running through a wire in an external magnetic field. But to do that, in order to understand what happens to a wire that carries a current in a magnetic field, we've got to know what a current is. We talked about electric charge in our last unit. We're talking primarily about static electricity, the buildup of electric charge. Current electricity isn't the buildup of charge, rather, it's the flow of charge. Specifically, the rate of flow of charge. By the rate of flow of charge, we don't mean how fast charges are going. Rather, we mean how much charge flows per second or per unit time. The analogy is this. You're standing on the side of the highway, your friend is standing on the side of the highway. One of you has a radar gun who's measuring the speed of the cars that go by. One of you is counting cars that go by with a stopwatch. The person who's got the radar gun is not measuring what's equivalent to current. He or she is measuring speed, how fast the cars are going, right? Are they going 80 kilometers per hour? Are they going 110 kilometers per hour? That's the speed of the cars. The person that's counting the cars going by, they're measuring what's equivalent to electric current, the number of cars per second that go by. Now, it's entirely possible to have a high current. Okay, if we stick with the analogy for a second, a lot of cars going by per second, but yet a really low speed. Okay? Your Deerfoot Trail, 5 o'clock, coming Deerfoot Trail south. Okay, it's bumper to bumper. There's a lot of cars going by in 1 second, but they're not going very fast. Okay, at 1 o'clock in the morning, there's not very many cars going by, but the ones that are going by are probably going pretty quickly, right? Speed and current are two different things. Speed measures how fast the electrons are going. Current measures how much of them are going, how many charges per second are going, the rate of flow of electric charge. Now, anything that's a rate, you learned about this in Physics 20. Anything that's a rate has time on the bottom. Velocity is the rate of change of position, delta d over delta t. Acceleration is the rate of change of velocity, v over t. Power was the rate at which energy is used up, energy over T. What's the electric current going to be? The rate of flow of electric charge. Tell me what the equation is. Kevin? Charge over time, Q over T. Now the symbol for electric current is the letter I. It's capital I. Current is equal to charge over time. What would the units be? Charge per second, or what's the unit for charge? Coulombs. So it would be coulombs per second. But something that means the same thing as a coulomb per second is an, I'm giving you a hint there, right? An amp, an ampere. Okay, we usually just abbreviate that as a capital A, but it stands for an amp or an ampere. Now here is what appears to be a ridiculously simple question. And you know what it is? It is a really, really simple question. It's so simple that the odds of you seeing a question like this on a test or on an exam are really, really, really small. But where you're likely to see this is as part of a larger problem. Later on today, we're going to talk about those wires with the current flowing through them in the external magnetic field. You may need to do this as part of the bigger problem. In itself, probably not. Part of a bigger problem? Absolutely. Let's see if we can handle this one. Calculate the current in a wire in which 20 coulombs of charge passes in 4 seconds. I'm going to say I is equal to Q over T. My goodness, I think I can even do this one in my head. 20 coulombs divided by the time of 4.0 seconds is going to give me 5.0. What are the units for that? We say coulombs per second, or we can say 5.0 amps. Both mean exactly the same thing. Just be prepared to recognize both sets of units. You can use whichever one you want. Recognize both. Yep. You do need to know it, only because they may give you the units coulombs per second sometime. So know it, but you don't have to use it unless you want to. Yep. Which one's standard? Both of them, because they both mean exactly the same thing. So both of them would be standard units. Okay. I think if you can handle that, I think you can handle these two, although, my goodness, this one involves rearranging that equation. But I think you can manage that. Give it a whirl, guys. We'll move on in about 1 minute here after you finish these questions. All right, if all those questions are, though both of those questions are okay, we're going to move on to the real purpose of this today, which is to analyze conductors that carry an electric current going through them in an external magnetic field. If you look at a conductor with a current going through it, you recognize that all we're dealing with here is moving charges again. If a charge goes through a magnetic field, and we know how to find the force on that charge, and we know how to find the direction of the force on that charge, then we can do the same thing with the wire that carries the charge. Because in the end, all that's happening to the wire is that it experiences a force due to the electrons inside the wire experiencing a force. Think about it. If a charged particle goes through the air through a magnetic field and experiences a force downward, then if the charged particle that goes through the wire through the magnetic field experiences a force downward, then so will the wire itself. All we have to do to find the direction of the field, the direction of the force on the wire, is the same thing as we have to do to find the direction of the force on the electrons that are moving inside the wire. And that's going to be the hand rule for deflection. Now, the equation that describes the force on the wire is a little bit different, but looks a lot the same as the one we've used for the charge. Here's how we find the direction of the force. Again, it's just a review because we've done that with individual charges. Here we've got a wire that's pointing into the page, and the electrons are going through that wire into the page. Let's find the direction of the force on an individual electron first. Thumb the direction of the particle into the page, fingers from north to south, the direction of the field. The palm points upwards, so the force on that individual electron is going to be upward. Now that's going to cause, it wants to cause that electron to go in a circular path through that magnetic field, but because that electron's in the wire, it can't. It can't go through a circular path. So what it does, as opposed to going in a circle, it just pulls the wire up with it. If there's a force acting upwards on that electron, then there's going to be a force acting upwards on all the other electrons moving through it as well. The force on all of those electrons combined are going to give us the force on the wire, which of course is going to be upwards. So all we have to do is exactly the same thing as we've already done. Hand rule for deflection, thumb, fingers, palm points in the direction of the force. How do we find the magnitude of the force? Well, the magnitude of the force on an individual electron is still QVB. But we're not usually trying to find the force on individual electrons inside a wire. Rather, we usually want to find the force on the wire itself. To do that, we're going to use a new equation, F is equal to I times L times B. F stands for the magnetic force, of course, and it's going to be measured in newtons. B stands for the magnetic field, and it's going to be measured in Tesla. What about I? Amps, you said, yeah, that's the units, but what's the variable? Yeah, it's going to be the electric current. And the units for that are going to be amps or coulombs per second. Now, you may have to find amps or coulombs per second by using the equation I is equal to Q over T. Or you might be given a value. Either way, it's not that difficult. Now, the last variable here is the letter L. What do you think L stands for? Yep. Length of what? Length of the wire? Yes. You got to be careful though. What it really stands for is the length of the wire that's part of the magnetic field, that's exposed to the magnetic field. For instance, Riley, if you have a 2-meter long wire and only 1 meter is in the magnetic field, the other meter isn't, it's outside of the magnetic field, what's the length of the wire that we use? Not 2, 1. We use the part of the wire that's exposed to the magnetic field. Now, what units do you think you're going to use for this? Meters, right? You see the value in this? Okay, you will see the value in this if you haven't already. If we apply an electric current through a wire and expose it to an external magnetic field, we can make that wire move. We can make the wire physically move by just running an electric current through it and through a magnetic field. That's a motor. That's an electric motor. How does an electric motor work? You run a current through wire that's exposed to an external magnetic field, it moves the wire. Okay, and that moving wire ends up spinning the drill bit, or ends up spinning the mixmaster blade, or ends up spinning the fan, or ends up spinning the wheel on your toy car. Okay. Now, the mechanics of it are a little bit trickier, a little bit more complicated than this, but this is the basic physics behind making anything that's powered by an electric motor work. Kevin? Yeah, you do. Yeah, you absolutely do, and we'll talk more specifically about the exact mechanics of making something spin a little bit later on here. For now, I just want you to know that, look, this is how we move the wire. Okay, we just got to move lots of it, and we have to move it in a certain direction to get a real electric motor functioning. All right, let's take a look at this, okay? 12.4, page 605. It says an 8.5 centimeter length of conducting wire. We're going to circle that centimeters because we wanted meters. Lies perpendicular to an external magnetic field of magnitude 4.2 millitesla. Here's the current. What's the magnitude and the direction of the force on the wire? That's going to be the length. This is going to be the magnetic field. This is going to be the current. We want to find the force. Did you notice when we saw that equation, ILB, you notice there was a little upside down T there again? What does that mean? The equation only works if they're perpendicular, if the wire is perpendicular to the direction of the magnetic field. They are here, it tells us. The current here is 2.10 amps. The length that's exposed to the magnetic field is 0.0850 meters. And the magnetic field here is 4.20 times 10 to the minus 3 Tesla. We get 7.497 times 10 to the minus 4 newtons. Or we're going to round that to 3 digits, or 7.50 times 10 to the minus 4 newtons. Remember, we could have calculated the force on an individual electron using F is equal to QVB. If we had the speed, we could have done that. But that's not what we're looking for. We wanted the combined force on all of the electrons. We wanted the force on the wire itself, for which we have to use F is equal to ILB. Now let's find the direction. Just find the direction on a single electron. Thumb in the direction of the particle into the page. Fingers point in the direction of the field from north to south. Palm points toward the top of the page. Kevin? What if the wire's at an angle? It'll still work, but that equation won't work. Okay? You'd have to use a slightly modified version of the equation. It's just like when the charged particle is going in at, say, 35 degrees. Okay? The analysis that we did didn't work anymore. We would have had to make a small modification to that equation to make it work. Yes, you would actually, yeah. It ends up being, you end up tacking a sine theta onto the end of it. That's all it is. QVB sine theta or ILB sine theta. That's it. Let's try these two questions, please, on page 605. What's the big word here in question number 2? What is it? Float. Yeah, the big word is float, right? If something's going to be floating, suspended, hovering, maintaining the same height, it all means the same thing. If that's the case, we're going to set something equal to the force of gravity. What will it be in this case equal to the force of gravity? Now, there's all kinds of forces, right? The electric force, the magnetic force. What kind of force are we dealing with here? The magnetic force. So let's say Fg is equal to Fm. Let's say mg is equal to, we're going to say ILB because we're not talking about suspending a charge. We're talking about suspending the wire. We're looking for the minimum current, I. So it becomes I is equal to mg over L times B. Put in our numbers here. 0.06 times 9.81 divided by 0.75 times 0.15. We end up getting 5.2 amps. Is that good? Good. All right. Here's your homework. Today's your lucky day. Worksheet number 13 for homework tonight. Okay? I think there's only 5 questions on it, so it shouldn't take you all that long. You can get a head start on it now for the next 5 minutes or so, and then finish the rest up for homework tomorrow.